He did ask on the selection of where the meeting is.
I told him 4240, I
Yeah.
think. Okay, now I remember. Okay.
Maybe it's just late.
Oh, no, I thought it was Anil who asked, not.
Yes.
Oh, Sheila also, okay, he asked earlier. Okay.
4:37.
Okay. Yeah. Do you want to take over, David? I mean, what did you guys like end up on something, or because you have you said you had published a new planet thing out there. Do you want to just show that or talk about?
Just show it.
Yeah. Okay.
You can just walk
I can.
through it, but,
Yeah.
yeah, there were just a couple of little fixes that.
Oh, I'm stuck outside. Can someone open the door? He's the pizza guy.
Oh, yeah. Make
Yeah.
sure you come.
Where is he stuck outside? I don't know.
There should
Is he
be
downstairs?
downstairs.
Huh?
Yeah, but that door is open.
Yeah, that door is always open. The main door.
Is it the wrong building?
Let me pull up that. I mean, you said you were discussing, what was it, you talked, you mentioned something. I thought, oh, wow, okay, you guys discussed that. What was it? This is the problem with this deep learning. You can't go back. I mean, it gets, yeah, autoencoders and stuff.
Yeah,
Very
so after
okay.
everybody sort of like broke up and started leaving, I was like, hey, I could show some people this. And
Oh, okay,
This is just
okay.
something else I've been working on.
Okay.
And so, yeah,
Okay.
so a few people stuck around for that.
Ah, okay. So that is after the thing.
Yeah,
Okay.
yeah.
Okay. Yeah, I thought.
kind of cleaned up more too, if people are interested in seeing it again.
Yeah.
Okay.
Yeah, I think we went through your notebook on the planet data set, and then we went through your notebook on the
Yeah, I mean, the planet data set, I mean, we can start with that and see. I mean, you said you've cleaned it up. So, is it, what is it? Scons? Yes, Pro, that's not you. Python scons, is that you? No.
Just go to github.com/David L. Martin.
Okay. What did he say? The security lock, but someone else was going out on his sneaking.
Yeah, that should be fine.
And if you scroll up in that deep learning channel.
Are you guys in the same room as last Monday? Yes. Oh, yeah, yeah. You've put a link in there. Usually it just gets wiped out. I just want to see.
Yeah. If you go fast, you'll see my picture.
Oh, yeah, there it is. Yeah, he said, I don't know. I don't think he was saying the security. I've just been, I've sneaked in through security and stuff. I don't know.
I don't know where he's at.
Where he is at.
Yeah, that should. Yeah. You may have to run this in front too.
It's security. They don't.
There's a lady at this, but she's like, go ahead. She doesn't. Oh, he's at the
Four people, and you have 5 people, six person.
It's about the same as last time.
So we all got food first?
Yeah, by the time, it'll take time.
Yeah.
Oh, you already ate it?
Oh, you brought, yeah.
Should I go to Google Colab and open it, or maybe we're not going to run it?
No, just open it here.
Yeah, yeah.
You can see it.
Are you eating?
You can't run it, but you can see all.
Yeah, all the stuff in there.
Stands and look, they're ordering.
Who's eating? Are you eating too?
No, I don't think I can open it on this. Let me just open it on I'll download it and open it.
Are you eating?
Yeah, I can eat, I mean, but, I mean, veggie.
Since Microsoft bought them, I have to click this 3 or 4 times now. I don't know. It's
Well, usually this 1.58, that's what makes it, because once you start putting graphics,
That's one of the things I really liked about GitHub was.
No, what I do usually is I go raw. Instead of that, I just go raw, copy it on my thing and then save it. I mean, otherwise I don't want to download your whole thing again because it's not easy to, yeah, download. Okay, there it is. I can download just this notebook. Well, it's not. Where is it?
Press Control S. Yeah,
So,
Control, save us.
Yeah.
Yeah. Oh, yeah.
What is that? That's 40.
Okay, why is that not? Okay, there it is. Let me just,
Text.
Last time it said you cannot, but when it delivers.
all files, then we can get rid of text. Yeah, it's a
does it
problem.
bring in all the images and stuff? When you load it in that way?
Yeah, it'll bring it up, all that. It has everything, all that information. No, I'll just open it there.
Yeah. RCS.
That should do it. Now go here. Lesson 2 Planet, this should open.
Yeah, so I added a bunch more sort of like, text. describing
Okay, yeah,
And,
it's good.
and I cleaned it up,
Took
used
the-
the latest version of Sconce.
Okay,
So since you've seen it,
yeah,
Narayana,
Yeah.
Sconce now has the ability to schedule any hyperparameter.
oh, okay,
So if you want to schedule weight decay to go cosine, or
Cosine.
go triangle, or linear, or whatever, or if you
Okay.
want to do momentum, or
okay,
any combination of them.
okay,
So this kind of shows off that a little bit. But
okay,
The thing that was causing errors
yeah,
was at the very end, I was using the wrong sized images to generate the submission to Kaggle. I was using
Hmm.
64 by 64 images instead of.
yeah, that's what he uses initially just to
Yeah,
speed up the trains. You train with this, I mean, that's what he mentions, hey, train with the smaller size image so that you're in the neighborhood, then you use the higher size image.
yeah, so I did the same thing.
Yeah.
But then when I went to go make the final submission to Kaggle.
Oh, yeah,
I used the wrong size images.
Image,
And then
yeah.
it was like, well, this
Yeah.
is trained on big images,
Yeah.
but I give them small ones,
Yeah.
it failed. And so now, it gets around 270th place out of, about 900. So
Okay,
It's
this
almost,
is pretty good. I
it's
mean,
like top third.
top third, yeah, yeah. What is the, I mean, do you get his kind of accuracy that he gets?
So I'm still a little bit less than him, and
Yeah.
I have like racked my brain on so
Yeah.
hard. I read through all of his code. I
Okay.
implemented a couple of things
Okay,
and then took them back out, like gradient
Okay.
flipping and
Oh.
using the k-meaning normal
Yeah.
initialization technique and stuff
Okay.
like that. But like I can't figure out what he's doing that is different than what I'm
Okay.
doing. The only
that's
thing,
that goes for your repeatability. That's the problem with that thing is people publish papers.
yeah, so
Oh, we're just looking at sandwiches or,
Oh, you can go back. There's a, yeah.
oh,
You go
okay.
back there, soups.
Not soups. I thought this is a pizza place or no?
This is a panini.
Oh, this is a panini
Yeah,
thing.
we're gonna
Oh,
switch it up, 'cause we did pizza last.
oh, okay. So you're gonna switch it up. Okay. Yeah, I don't think I can eat a whole thing, but I mean, if somebody is willing to,
I think we will, a couple of people might come.
Might
They
come.
also just-
Okay.
Like the peak two or something and.
Yeah.
the half, someone else will- I'm sure by the time we might feel hungry.
Mediterranean. I mean, the only thing I can order is the Mediterranean veggie here, so that's the only thing. So should I just add to it?
Yeah.
Mediterranean veggie? Yeah. Okay.
And then we usually comes the way, so.
Oh, okay. Oh, you're already having food. How can you?
Trying to go. And I don't think this will work. But I'll not be here next week, so.
Okay,
The food.
yeah.
I'll be
Well,
Decatur.
where? Decatur?
Yeah.
Oh,
Into that village.
where?
Decatur.
Decatur, Illinois, isn't it?
Yeah, we are.
Where is, oh, that's near Chicago. Yeah. Now
Yes, 2 hours.
Two-
2.5 hours from here.
yeah. Yeah, in between Chicago. Yeah. I remember going on the train passing through Decatur, Illinois.
So
Yeah.
hopefully you'll have the.
Oh, yeah. Oh, yeah. We'll have the online thing. Yeah. Yeah.
I'm actually going to go to feed you
Yeah.
guys.
That's okay.
That's all.
Yeah.
Funny today. The same dollar amount.
So, well, it's just, so you've done all his affine and resize and horizontal flip. Have you done his all his transformations that Jeremy did? I don't think so, because he has some few tricks.
Well, he completely rewrote all of his
Transformations, yeah.
So he, like specifically in the lectures, calls out PyTorch, the Torch Vision library. He's
Yeah.
like, I don't like the Torch Vision, it's slow.
Oh,
It
yeah,
relies
that he
on-
mentioned
It
something.
relies on Pill, and Pill
Yeah.
is slow, and he rewrote. a
So
whole bunch of
he
stuff.
was saying Pill is slow, and then he said the other one he's using, which is faster.
OpenCV,
Oh,
And then
OpenCV.
they switched off of that too, I think,
Oh,
later,
okay,
but I'm not sure.
okay.
So don't quote me on that.
Yeah, he's rewritten all that transformations. I saw that. He
So
has a
I'm assuming
transform.
that my transformations are fine. I mean, I looked at them and, they're, just pretty standard
Yeah.
stuff. So it's little slight rotations, slight shifts.
Yeah,
slight,
no, he has this, what is it he does? The 90-degree rotation or something he calls that. He has a name for one of the rotation I saw that he uses specifically. Dihedral. Yeah. So that's what he uses it specifically for that planet data set, the
Yeah.
dihedral rotation.
But I think
So-
that's equivalent to like a horizontal and a vertical flip.
Flip is
That
like
gets
this,
you all
like
the
this.
different angles. Yeah.
I think I don't know,
mean,
the
they're not
flip is exactly the
identical, but
same,
it's
yeah.
like basically.
And then he uses the TTA, test
So
time
the TTA,
augmentation.
but even before TTA, he's getting better results than what
Then-
I can get.
Okay,
Like I get really close to his results, but
Yeah.
for some reason his network just continues to train a little bit better towards the
Okay.
end. Like
okay,
mine gets down to like pretty close to where his, and his just keeps getting a little bit better over time, and mine doesn't. So-
okay. So this is transformations you've used and then this is the standard stuff.
Mhm.
And yeah, the data generator and the test data generator and class balance. Yeah, he talks about, but here you can't
So I
do much
tried-
about the
I
class
spent
balance.
A couple of days doing
Oh.
class rebalancing.
Really?
and
Because this
it
is
always
multi-label. I don't know
works.
how you do a class balance and this is a multi-label. Each picture has
So,
multiple things. If it was only one label, then you could probably do
Yeah,
away
so-
or simulate and stuff like that.
so what
But
I did was I went through the entire data set and I gave every image a score based on the inverse of its frequency of all of its
yeah,
labels added up.
okay,
So things that are like on the list there, the things that are the mines or the
Yeah.
blown down or whatever, like conventional line, those things that are really, really tiny,
yeah,
it gives those a higher score. And so those start showing up in the data set more often.
mm,
And the ones that are still super common stay super common. But it really just kind of like brings the floor up. And so
okay, okay. You're just, whenever it sees the batch, the mini batch, you're trying to bring up these labels, which have
Yeah,
these
I have a
labels more.
notebook that shows it too. I just
Okay.
don't have it on GitHub right now.
Okay,
But
okay.
it always made the results worse.
Yeah.
Like it never made it better.
Because
So-
how do you then determine, because a lot of pictures have primary plus something else. So are you just saying, hey, if it has that something else, bring it more than the primary alone or,
I'm just, I'm going through image by image and saying,
yeah.
if you have one of these rare things,
Mm,
you have a higher chance of being in a mini batch than if you don't have the rare things.
rare things, okay, okay.
And so,
Okay.
like, it just makes this distribution so that it doesn't have those.
I mean, it's kind of a weighting thing you're giving to it and seeing,
Yeah,
okay,
it's,
yeah.
it's
So that it brings it
trying
more,
to
yeah.
unbias the data set,
Data set,
assuming that
yeah.
things happen in the same frequency. But I think
Yeah,
maybe the
assuming,
network
yeah.
itself is learning
Learn,
that conventional line is rare.
Yeah,
And so maybe I shouldn't
do that, yeah.
do it if it's more rare or something. So
And then
that's my
this
guess.
is
I
the,
don't know why it doesn't make it better.
and then he used his adaptive average pooling then.
No,
Or-
so this is a standard out of PyTorch. I did use his adaptive
Okay,
concat pool.
Concat
that
pooling,
does-
yeah.
But that made no difference.
okay,
So I took it
okay.
back out.
Okay,
But yeah, his concat pooling is the max pooling and adaptive average pooling
pulling
concatenated together.
Together.
So max and average together.
together, he concatenates it, yeah.
But it didn't
Yeah.
make any difference, so I took it back out.
Oh, okay, okay. But
And he
you
used
put 'em-
dropout and I didn't, and it also didn't make any difference.
Didn't do
So-
anything, okay. But you have two, you had to use two fully connected layer here at the end?
Yeah, so the layers are the same in terms of the sizes and.
Yeah,
and
same, yeah.
The only difference
Only thing is I see there is a relu here and there is a sigmoid here.
Mhm.
Okay,
Just like his.
okay. That's what, so he uses actually two fully connected layers at the end? Okay.
Well, I mean, the last layer is your prediction layer.
Yeah, last layer is prediction layer. That's what I thought. I didn't know there was another layer before that that was also fully
Yeah.
connected.
Mhm.
Because if you look at the RESTnet, they usually, I thought there was a fully connected layer at the end called FC.
Yeah, he replaces it with two layers.
Two layers,
Yeah.
okay. Okay. Yeah, which is the same, okay, the mid-size, how did you choose this mid-size? Is that different from the, I mean, that's gonna be different from the inside, isn't it? So it's like choose.
It's half. You can see it on the.
Oh,
bottom.
half, okay, yeah, right. So you're just taking that size, it comes out of the average pool and then half it, and then from the half, it goes to the number of classes,
Yep.
okay.
What's a fully connected versus?
So a fully connected
Yeah.
network takes all of the previous layers activations. And so for every activation in your fully connected network, there's a weight that goes to every single.
Yeah, if you look at that, where's
Oh, you can just write on the walls in here.
Yeah, oh, there it is. Yeah, we can get on the walls. I mean, a fully connected layer, if you have this, and how many, I mean, the hidden, each one be connected here.
Yeah, I'm not
And
sure
this
which
one-
direction you're drawing things. I
No,
can draw
this was the input. I mean, this was us thinking the inputs. I mean, if you have so many inputs, I mean,
so if
data
is going in this direction.
yeah. Oh, yeah, this I'm going in this direction.
Then this
Yeah.
is fully connected. So that's every possible
It
connection.
depends, I mean, it doesn't have to
So
be three,
these
you
are all
can
weights.
have more outputs than the inputs of the.
Sure, yeah, I could do
You
four.
four and stuff. Yeah, that's what I was trying to, yeah.
So, yeah, so this is out.
And
and this is in.
previous layers are convolutional, well.
Could be anything.
And the
Yeah,
same
and in a convolutional layer, you have some kind of a structure. And then you have, like this would maybe only,
Connect to,
it would have weights based on its filter and the
The-
filter kind of slides
So the
across.
nine, in case 3x3, it will be connected to nine only.
Well, not exactly
No.
to 9 because it slides across or whatever, so it's,
But that particular point.
Yeah.
Would be
No.
connected to the main nine.
what do we?
each pixel in this,
If you are talking about pixels, yeah. It would be connected to nine.
You connect it to less weight, there'll be less weights in a convolutional network
for
than
sure.
a fully connected layer.
Mhm.
Because each one, however many outputs you have, that
Yes.
many weights you're gonna have. for
Yeah,
each-
so
each
depending
input.
on which one you are here, so let's say these are two layers and they're just one dimensional instead of two dimensional. But a convolutional network might look like this,
And
wherever.
That's exactly it. And-
And
then if you
Yeah.
compare a fully connected to convolutional, that means the kernel would be the full size of the year.
yeah.
It's
Yeah,
connected every pixel,
usually though,
to-
with the kernel though,
I know, it's different.
you would slide it across or whatever, and you
I mean, you
can't slide it because.
There's no
it's-
sliding, it's just every weight is distinct. There's no sliding, everything is connected to everything else.
Yeah, so it is true that a fully connected network is a superset of a convolutional.
That's much more expensive to
Oh, yeah,
relate all of those.
oh, yeah.
Yeah, so but typically when you do a convolutional, you have in filters.
Yeah.
And so it's like in copies of these horizontally.
Yeah.
And so they end up being like
Okay.
more computationally expensive, but less expensive in terms of the number of weights you have to store and keep track of.
So in a convolution layer, those inputs, depending on what the features are important, like for recognizing a dog, maybe it's the ears and the cats.
Yeah.
Those connections are stronger for which are, the inputs for the dog or cat or whatever it's trying to recognize, right? But are those just the weights or is that the connections too? I don't know if that makes sense. Like, how certain features of the image are important for certain objects?
Certain objects,
So are those connections based on that or is that just the weights being bigger and stronger?
I'm trying to figure out how
No.
this is another simplification that we didn't, or another sort of thing that we didn't mention here, is that if we say that this is W1, and this is W2,
and then
this
W1.
is W1 again.
Yeah.
And this is W2.
Two again.
So these are shared across.
Oh, yeah.
So there's even fewer weights than you might think, right? Whereas these are all completely.
They have a ton of them, but also one card.
The way the convolutional network was able to figure out, they figured out, because each pixel is not important at all in an image. One pixel has nothing. But each pixel is different. They said, yes, the pixels are defined, any neighboring pixels is what, if I take a 3x3, that defines something. The neighboring pixels, how they change color between that established some relationship. So there's no point just going by pixel and connecting into a fully connected layer. Okay, what do you learn? But you're trying to learn some areas and stuff. Hey, the 3x3, 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 is it different? And then they said, well, I can't have just one set of weights because one set of weights will learn something because it's all randomized. These all start at the randomized. So they will start learning, one set of weights will start learning some features, and then the next filter's weight will start learning something else. And then the next set of filters, that's why they put like 20, 30 filters there, so that each filter has a chance to learn some feature in that image. And since they start at different starting points because of the randomization, they will end in different places. That's something, it took me some time to figure out, okay, why does the convolution, why do they have so many filters? Because they want to have the random thing and have that.
Think of each filter as a feature extractor.
Exactly, yeah.
And that filter slides across the input activations and tries to match on a feature.
Yeah.
And it creates a new set of activations that is sort of like, where did that feature show up in the image? And so that's why they have so many filters, because they have so many features they want to look for. And then features of features, because as you move deeper into the network, you're not looking at input pixels anymore. You're looking at you're looking at activations of previous layers.
Previous layers. There is no, at that point, there is no pixel. We have lost that. You can't define a pixel. Yeah, it's something. It's something, and then they visualized stuff. We have gone through that where the people have visualized what happens into each layer, and what they found is the initial layers find all these edges and corners and lines and all that stuff. And as you get deeper and deeper near the end is where it starts recognizing the images. That's why we replace, when we do the transfer learning, we replace the last set initially, because that's where we think it starts recognizing the classes and we can replace and do the transfer learning. And then we go back and try to say, okay, let's unfreeze the previous layer and start learning. That could improve it a little bit, and you can unfreeze a little bit more and stuff. So
yeah, so if you think of those filters as feature extractors, the features of natural images are mostly the same if you're looking at just pixels.
Yeah.
It's like bars and lines and some gradients and stuff. But then as you get deeper into the network, they become more and more specific, because maybe your data set didn't have any satellite images in it. And so that's why we train it with higher learning rates for the deeper layers than for the shallow early layers. At least that's the idea. I don't know.
Yeah.
Like if you trained up a network from scratch, which is how everybody when you get your pre-trained network, it was trained from scratch, right?
Oh yeah.
So if you train the network from scratch, you don't do this different layers have different learning rates. I don't think anybody does that. They just let all the layers have
all the layers have the same learning rate initially.
Yeah.
I don't think anybody does.
So,
even his thing where he shows the ResNet at the end, which I was looking at today, and where you start with a few layers, he just used one learning rate.
So I don't know
For
why
all
we
the
don't
layers.
end that way at the end of the maintenance and the cats and dogs data set. Because once you've taken your new classifier, stuck it on the end, trained it up so that it sort of matches the rest of the network,
Yeah,
why don't you then just train the whole network with the same learning rate, just like at the end of the pre-training? That's how they were doing it.
yeah.
I don't know.
I don't know. I mean,
I haven't tried
he
that,
intuitively,
but-
he appeals intuitively, well, I don't want to change those things as much or things like that. And he wants to use a lower learning rate. We don't know why he just says that's kind of as a heuristic out there. I don't know if it's really needed.
Yeah, but I mean,
yeah.
maybe it starts to overfit.
Yeah,
Like, these networks have millions of parameters, and
yeah,
if you don't have a very large data set, it can overfit pretty
Yeah.
easy.
crazy, yeah. Yeah. So, okay, so this is the forward was, did you construct, this is not your own model, isn't it? You were just going to use the ResNet 34. But-
This is just me tacking on to the ResNet.
ResNet 34.
I'm rerunning all the same layers that they do up through layer 4, and then I add on the new classifier.
Okay, you just didn't use the way we have done in the past, where you just use the PyTorch ResNet 34 and then just decouple the last layer and then attach the.
Yeah, so what we were
yeah.
doing before was like monkey patching.
Yeah,
What they called FC
Yeah.
into whatever we want it to be.
we wanted to be, yeah.
And the problem with that was that there's two things that happen after layer 4. There's FC and there's an average pooling.
Yeah.
And I wanted them both gone. And
Okay.
so,
Okay.
I mean, I could call my new thing average
Yeah.
pooling.
Oh, yeah, yeah,
But it seemed
yeah.
like sketchy.
Yeah.
And
Yeah.
the way they do it in the FastAI library
Yeah.
is
No, they've written the whole
they
thing.
just treat it all as an array.
Yeah,
And then they split the array into 2 parts.
Yeah.
Well, it turns out that when you build a new nn.module class,
yeah,
the order in which you define your layers
yeah,
is the order that they go into that array that they split.
yeah.
And so if it were the case that the ResNet people happen to, like if you go to the,
Where?
can you look at Torch Vision's GitHub?
Okay.
Then you can see the ResNet definition. But if they had happened to define things in a different order, then all the FastAI code just starts to break. Like, you could just reorder 2 lines in FastAI. Well, I mean, breaking, it still
Yeah.
runs,
Yeah.
but it would like start,
Torch
why actually might start
Vision,
crashing.
ResNet 34.
So look at the double under init on,
Yeah,
well, look for the place that looks like mine. So it's doing, so scroll down a little ways. That's just a
Yeah.
block.
okay. Oh, that's the basic block. He
That's a
defines
block,
that. And then he talks about a bottleneck block later on in the last lecture, but then he said, let's not get into, because he's building a ResNet and he
So-
says the bottleneck, he says we won't get into that.
Those bottleneck blocks only come in for the really big ResNets, so ResNet
Okay.
50 and 101.
Oh, okay,
Okay. For the 34 and 18 ResNets.
Oh, it doesn't even come in, okay.
But here,
So here's a ResNet, yeah,
so here's ResNet. So you see all this self layer 1 equals, self layer 2 equals, self layer 3 equals. Like if you just switch the order of those, FastAI library will break. Because it's relying on the fact that like PyTorch internally, every time you define one of those, it's
Yeah.
going through in the class constructor.
yeah,
And it's like adding those to an array. And then the
Okay.
FastAI library just takes that array and splits it into chunks. And that's how he comes up with his 3 different
three different things.
learning rates.
Yeah,
It's
oh,
just like splitting
yeah,
an
I
array
saw
into
that
pieces.
and I said,
It's
forget it,
really
I was
hard to figure all
rewriting,
this
yeah,
out,
it's, yeah, okay. The way I was doing it was, hey, I just took, when I was doing it, I just, where's this?
So anyway,
Yeah,
this is way into the weeds and I apologize if I'm. boring.
no, but this is something I thought, I mean, let's, the thing was, I was actually going and saying, hey, layer 3, layer 4 unfreeze, and then putting a learning rate into that, because yeah, his thing you can, I mean, he does something called, he defines some layer, there is a layer class or something he defines, and I don't remember the exact name, but he
They
has
have
a
something called a layer optimizer.
layer optimizer. Yeah.
Yeah.
I just couldn't, I mean, so, okay.
Yeah, so Sconce has an abstraction called a parameter group.
Okay.
And the model defines its parameter groups.
Group, yeah.
And so later on, you'll see that I define parameter groups for each of the layers.
Okay, so you're going to define whatever is being defined in ResNet here? Is that what you're defining?
Yep, that's what I'm in the forward function. So if you
Yeah,
look at
here,
their
forward function, yeah.
I just use that forward function
Okay.
up to the the average pool.
Average pool,
Because
yeah.
I want average pool in the view in the FC gone. I
Okay.
just want up to the layer 4.
And do you define an init here? Okay. I mean, you're going to just say it's the base model, basically.
Base model plus the new classes.
Plus the new classes, yeah. Okay. And then they calculate the loss and stuff that we've done before, the cross entropy and then the metrics, yeah. Yeah, okay. And then here is where we use using the F-beta score.
Yep. Yeah, so another difference in his code versus mine that didn't make any difference here was this threshold.
Yeah,
His
the
code
threshold
actually
point
tries
too.
a bunch of thresholds,
Yeah,
every single mini batch. So every mini batch is getting a different threshold potentially in his code.
how do you, but then at test time, what do you use
I
then?
don't know.
Okay,
At test time, he does the same thing.
yeah,
I mean, he doesn't have to tell it. Like at test time, I think he has to like define a threshold.
you have to define a threshold and then that's what you make the prediction. You can't just use a random threshold.
He doesn't go all the way to actually making the CSV and submitting it.
No, he
My
doesn't
code
do that.
does,
Okay, no,
which
he
is-
doesn't do that. I mean, he just
Which is
goes and
maybe nice
says,
for people in the class. If you run through
Yeah.
this notebook, you'll go all the way to making the CSV that you
Okay.
can submit to Kaggle
Ah.
and get a score.
score. And then we can try to add a few layers and see if we can get a better score.
Yeah.
So,
No, if somebody can
Yeah.
figure out what things need to be tweaked to
Yeah.
make it better, that would be awesome.
okay. And then the trainer generated the same, yeah, we've seen this before. And then the learning rate about, still, yeah, the 0.1 or something. So,
Mhm.
and then you used a triangle way to, okay,
I just used what
scheduling
he
it.
did, which was these cosines.
Cosines. Oh, okay. I thought I saw triangle here, but Learning.
Yeah, I think that was just a mistake that I imported that and didn't use it. Yeah,
Oh,
That was
okay.
probably when I was like going back and trying
Okay.
different things. I
Okay.
tried the triangle, and I
Okay.
tried different things.
okay. And then the layer wise is what you're talking about here.
Yeah. he
Different
ended up-
learning rates because you said, yeah.
He ended up changing the name. So at first he called them differential learning rates.
Yeah.
But then somebody pointed out to him that differential means something in mathematical terms.
Yeah.
And so now he's like, I don't know what he called them.
Okay.
But I came up with just layer-wise learning.
Okay.
So. Yeah.
Freeze.
So this is where
The unfreeze thing.
You
Yeah.
can freeze these parameter groups, and you can set individual schedules for each
Yeah.
parameter group. So I think it's pretty easy to understand kind of what's going on,
Yeah.
and as flexible as
Why is
FastAI
the
library.
freeze? So the freeze is a function which I just only unfreeze the layer 3 group, isn't it?
Yep.
But why is it having layer 1, layer 2, layer 3, 4?
So I want to
layer one?
freeze the whole everything except for the new classifier,
Okay.
or unfreeze everything.
So that's just a define, okay, that's not part, okay, that's a blanket freeze. If I wanted to say freeze, I can freeze the whole model.
Not everything. It's everything except for the
For your, yeah, the
new
new
classifier
classes,
that we put
okay,
in. Yeah.
okay.
And that's what he does too.
Okay, but this unfreeze comes as part of PyTorch, this torch
No,
vision?
that's part of my parameter group abstraction.
Oh, okay,
So the parameter group will freeze all of its
okay,
parameters.
okay. So that's your accurate, the loss is 0.16, val loss 1.14. Okay. Because I thought he got close to 0.1 or 0.89 or accuracy or 0.89 kind
At
of
the
thing.
end, yeah,
At the end.
he's a little bit below where I am.
Hmm.
In the end, he ends up with remarkably.
Oh, you've got a loss like this. Okay.
Yeah, no, I get, so at the
Yeah.
end, I get 92.2
Okay.
and he gets 93.6.
Hmm.
His 93.6 can't be real though, because if he submitted that, he would win the competition, like first place. Because 93.3 is what won the competition.
Oh, okay. Okay.
So I don't know what's going on with his, like,
Yeah.
but in terms of losses, like the actual loss function
Yeah.
values here, I'm not quite as good as his. And the people on the forums who said.
What do you mean the loss function is not quite as good as this? Which,
No, I just mean that his model is better than mine, even if you don't consider accuracy. If you just
okay.
look at the loss, which is what you
Yeah.
were doing.
Yeah,
then
I was just looking at
he
the
gets-
loss.
He gets a lower loss
Then even point
after
out
training than I do.
okay.
And so, and that is also consistent with the people on the FastAI forum who said they used the FastAI library to submit to the competition and they got around 100th place. And I get around 270. So like it is,
Well, you don't know. The thing is, things change during, I mean, they would have submitted last November or something like that. 100th place.
yeah,
You don't know. Now 270 is what place. It could
That's
be
true.
because a lot of people are submitting. And
well, I
If
don't
somebody-
think the new submissions don't count. So the competition closed
But
8
was
months
it-
ago or something.
yeah, but it wasn't open when they were doing it either. When
Yeah, so
Jeremy
the-
was
the
doing, so
places
they were, that's what.
Are real.
Huh?
If they said they would have got 100, then
Oh, it
they would
doesn't
still.
count
Oh.
against other submissions that happen after.
Yeah, my new submissions don't actually get a place in the scoreboard.
They don't get a place in the, you can't, I mean, okay, this is not a competition where you can do late submission and still,
You can
Be
do
on
it
the-
and you get a number, but it
Yeah.
doesn't put you on the scoreboard.
hmm.
The scoreboard's like frozen and you can
Oh.
find where you would be, which is what I did. Like, you have to
Okay.
just scroll down and be like, oh, that would have been here.
Okay, okay.
But
It
that
actually doesn't
it's
put
not
you on
exactly
the,
the same, yeah.
okay. Yeah, then if they said it 100 and stuff, that's a different thing, yeah.
Yeah,
Because there are some Kaggle competitions where you can, I thought you can put yourself and it'll score you, even after the competition is
yeah, it
closed,
still
yeah.
scores you, but it won't put you on the ranking. So
Okay.
It doesn't rank. So here you can see that I'm using the different layer-wise learning rates.
Okay. Okay, the layer
So
4,
blue
layer,
is for the new classifier.
Classifier.
And the other colors are the
other
shallower
classifiers.
layers.
Okay, so you didn't change, you only changed the learning rate after the first cycle?
No, so at first you only train the new classifier.
Yeah, yeah.
And then you train everything. And then you
Okay.
up the resolution and you do that again. You only train the new
Okay.
classifier and then you.
So
train-
you've automated this whole thing then? In your stuff, it goes through that? that it
I mean,
first-
it's
It
not
does
exactly
this?
Automated, it's in the cells.
Okay,
But this is like showing you sort of visually
Yeah.
what it's doing.
okay.
But yeah, I mean, there's lines in there that freeze it and then train.
Oh,
and
yeah.
Freeze and then change.
Freeze
the
and
resolution.
Oh, okay. When it is running the epoch, you're saying how to do that?
Yeah, so,
Changing it, yeah,
so what I do is I up the resolution of the generators.
yeah,
And then I freeze everything but the last layer. And then
okay.
and then I train, and then I unfreeze, and then I train, and then I do that again.
Okay, okay. I'll certainly run it.
All in all, I
This
don't think
week.
it's that much code, and
Yeah.
like a bunch of it's repeated towards the end. It's just
Oh,
like
yeah.
do it and repeat it.
Repeat it and doing things differently, trying a few things different and all that. And okay,
Well, I mean, this is just one shot straight through, not really trying anything different.
okay,
All the experimentation I did, like outside of this notebook.
okay, okay. Because now you're starting to is this the loss? No, yeah, overfit a little bit.
Well, you look at the
Yeah.
lines to see if it overfits. So
Okay.
yeah, you can see towards the end it's overfitting a bit.
Overfitting a bit, yeah.
Yep.
Okay,
And so I don't know if maybe more data augmentation would be key. I didn't use dropout, so maybe dropout would help a little bit,
Yeah,
but I didn't like
okay.
it. After I added dropout, it didn't make a difference in terms of the final accuracy, so I just left it out.
And the key thing is you're also using the, what is it? It's not the loss function is here, which is,
Yeah, so
oh,
just
we're
binary
using the
cross-entropy.
binary cross
So
entropy, not
that was
the,
the key. So
oh,
I used.
not that other one?
Yeah,
Remember
so
there is a soft,
that's-
a multi-label softmax or something like that?
Yeah, that cost me like 4 days. So.
Oh, okay.
So like I was changing everything.
Yeah.
To matches, and I just couldn't get even, like, I couldn't get above 89%.
Yeah.
Accuracy.
Yeah.
And then I dug through all of his code and found out he's using binary cross entropy.
Hmm.
And I
So
switched
you
it,
could,
and then all of a sudden I'm like 92.
so you could just use a binary cross. Okay, I didn't know that. Okay, that's good to know.
Yeah.
Binary cross entropy. So that's different from the normal cross entropy, is it? I mean, how does it deal with the multi-label thing? Because each one is
Each
going to.
one is considered separate. And this
Okay.
is the same loss function, say, used for an autoencoder where you want to do pixel-wise loss.
Okay. That's good you found it. I wasn't able to find his loss function, and so he's just using a binary cross entropy. Okay. Because I was using somebody else in the Kaggle competition had said something about that soft margin loss.
But it only
Yeah.
gets you about 89% accuracy. The
Okay.
loss function is maybe not
It's critical.
enough or something. I don't know why it's just not as robust as binary cross entropy is.
I'm not seeing the binary cross entropy is not defined here. Okay, I just wanted to see what it is using.
Sure that it's just the cross entropy, and then it switches P and Q. So it's sort of like a harmonic average of the two treating signals.
I think I'm back to the same thing. Creates a criterion that measures the, I'm back to the same thing, F dot. I need that F dot binary cross entropy. Because binary, because this is multi-label class. Okay, I'll look at it later. I mean, that's something that's good to know. You know that how it's dealing with, because you're gonna get multi. Yeah.
Because you're using
Because
the
you're not
Sanborn
using
instead of the softmax.
Softmax, yes.
You have every one of them is between 0 and 1, and they don't
Yeah.
add up to 1 anymore.
One anymore, yeah. So you can't use the argmax to find which class is the max and stuff, and you're using the threshold for greater than 0.2 and finding all the classes that are, so you'll get multiple things that are more than the 0.2, everything, and then it's doing a cross entropy, binary cross entropy on that. Okay, okay. I don't know why this multi-label, that soft margin loss was suggested. I mean, they mentioned that if you go to PyTorch, that torch vision loss, I mean, that's what they say use for multi-label thing.
Yeah.
Okay.
It could be the case that that threshold was in some way related to the loss, so that maybe a different threshold would have been better for that kind of loss.
Kind of loss,
Or maybe
okay.
that-
Okay.
But
Okay. That's something, I mean, it's maybe, I mean, you or you should write about it in the thing. I mean, those things are not, I mean, just checking the planet data set, those things are not obvious. I mean, you go and try to find out in the FASTA, it's not very easy to go and find that he used the cross entropy, binary cross entropy there.
Yeah, I mean, I think that's fine for his style of
teaching,
He
yeah.
wants to teach you, like, here's the state-of-the-art model, and here's how you can do it in 4 lines, and then later we'll
Okay.
talk about it.
Yeah.
But he never actually gets around to
the nuts and bolts of it. I mean, he gets into nuts and bolts only in a very, I mean, like as I said, the RESTnet, he does build 1 or 2 layers of the RESTnet and says, okay, how do I build this RESTnet? And he goes through the theory of, okay, what does the RESTnet do in effect? and then he uses the batch norms, he uses the con batch norms, and he repeats it and says, okay, we're going to use that, and he trains it on a CFR and gets decent result. I mean, he's saying, okay, this is only 2 layers of ResNet, so I'm not going to get a result, but he says 4 years back, that was state-of-the-art result of 85% or something. So, okay. So should we talk any more on this, or I mean, and it is few things we hit on. The last function was good, and the way he's doing the different learning rates and how he's doing the cosine alignment, that we have seen that before, those techniques before. And submitting to Kaggle, I mean, at least all of us should try to submit to Kaggle and see where we got, what we got. And we can try a few transformation. I mean, you're going to just play around with the main things we can play around with the transformations, the threshold, maybe.
How long to train for.
How long to train for.
Yeah, what
and,
learning rates to use.
To use, yep. And different learning rates, and see if we can get.
See that everybody gets over the initial sort of technical hump of actually running a notebook.
And see if it is repeatable. Whatever David has done, I want to see if I can repeat that. There's a lot of things like you're saying, you cannot get fast AI things. I want to see if I can get that repeated if I start with a different, random, I mean, because I'm going to start with a different random, I mean, the layers that you've constructed, I'm going to start with a different random positions. Am I going to converge to the same solution? I'm going to get exactly the 0.9. I mean, hopefully.
There's a little bit of, so if you run it multiple times, you get a little bit different result, but
yeah.
It's usually really close.
Really close, yeah. You should get in theory, yeah. You should get close. And freeze layer, yeah. And then the thing is to see is what is it getting wrong?
Yeah.
That's what may tell us what we are missing.
Maybe. I mean,
because 10% of the time it's getting it wrong. At least just saying, I mean, it's not 10%. That's high level. I'm just saying you got 90% accuracy or something like that.
So
and so what is it?
People who won the competition got 93.3.
Yeah.
We get 92.2.
Okay.
So they're doing a bit better.
Yeah.
But I don't know what they're doing that's different than us. The only thing I haven't fully explored is this weight decay issue. So there's been a bunch of talk in the PyTorch forum.
Yeah, that's something I wanted to talk about. Yeah.
Atom has been, the Atom optimizer has been using weight decay wrong for a couple of years.
Oh.
And with stochastic gradient descent, the standard algorithm, weight decay and L2 regularization are identical. But that's not true with Atom or in general. It's only true for the standard way that SGD is done.
Okay.
And so somebody in the FastAI course noticed this and started putting in a patch to PyTorch, but it's still open. It's been 6 months. There's been a PR 6 months. The thing to look for would be SGDW or AtomW. If you look for PyTorch AtomW, there's an open GitHub issue. And it may be the case that FastAI has already got it implemented, and that's what they're doing instead of the standard SGD. They're doing SGDW, which properly accounts for weight decay.
Atom, not SGD.
No, both. So,
okay.
So
it's wrong for both?
Yeah,
in PyTorch?
well, I guess with momentum it's wrong or something.
Yeah.
I don't know all the details. I'm still struggling.
Atom SGD is what I need to put?
AtomW.
AtomW.
And SGDW. AtomW would probably be good. There you go.
Okay.
Issue. And then, so the issue's open, and I think there's pull requests out about it, and they've linked to papers and stuff. It's a whole long thing.
I mean, is it really true that it is, Okay. It is wrong. I mean,
So.
is that,
So there's been a long-standing like everybody who does like ResNets
yeah,
and image classification knows we just use SGD, we don't use Atom. Because it turns out that you can't quite get as high accuracy with Atom. And everybody's just like, there have been papers written about like, why is it? And it turns out that some people think that it's because the weight decay is implemented incorrectly in every major library.
oh,
TensorFlow
it's
doesn't
not
count.
just PyTorch.
Yeah, it's
Oh.
everybody who's ever, like, because that in the Atom paper, this is how they said to do it.
Yeah.
And it handles weight decay incorrectly. It makes assumptions that are not true.
Hmm.
And it has something to do with how weight decay and L2 regularization are not the same,
Okay.
but they are coincidentally the same for standard SGD with no momentum.
Okay.
I don't understand it still.
This,
And that's
I mean,
the
does
only rabbit
everybody,
hole
I mean,
I don't
okay, we are talking, people may not understand what that atom is in SGD,
Yeah.
the difference, so
That's good. We should-
I don't know. I mean, that's one thing. I mean, he had something in here. I thought he had
He's
some,
definitely using SGD.
no, he had some Excel things which describe
Oh, yeah.
atom and stuff, I thought.
Gradient descent right there.
Yeah. Well, download it. There's no way to see an Excel file on. Just,
Anyway, all that was just to say that there's this
Yeah.
one rabbit hole I haven't jumped down, and that
Okay.
may be the difference between FastAI library and Scott's. But it was a deep rabbit hole, and I was just like, I'm gonna move on to do other stuff.
oh yeah, yeah. Yeah, this notebook, if you got, I mean, we need to look at this. This is where he talks about all the differences between all these different things we've been talking about, the basic SGD and what is the momentum and what is the AdaGrad, and he gives examples in Excel and how they work and how they how that optimizer function works. I mean, the basic SGD is what we use normally. Not even if we're doing, we would evaluate all our and then update the weights. What makes it stochastic is the SGD, is the stochastic part of the gradient descent. And then he does this by combining a decaying average of previous gradients with the current gradient. It's
Do you
all
know
these
what
things.
lesson he covers that in? Is that 5 or 6 or something?
Does he
Later in-
cover that is the question. I've looked at it. I don't think he goes into,
Really?
does he go into that? I mean,
He definitely did in the 2017 version.
2017 version, he definitely went into that.
Maybe he didn't have time in the 20.
Yeah, I just don't know whether he actually went into that. The
That
optimizers.
was in the lesson 2 part 2 of it, wasn't it? When he comes back.
Oh, maybe.
No, here?
No,
Here?
remember, he has a part 2. Then he
No,
comes
part
back.
2 is advanced.
Yeah, I thought that's where he comes back.
No, those are advanced stuff where he goes through where object detection and stuff and NLP. He talks about language translation and then he goes through the GANs and stuff, things, just style transfer and all that. I don't think he taught, yeah, I remember because he went through in quite detail in the previous deep learning course. But in this deep learning course, because I was looking at it, because he talks about overfitting, embeddings, NLP, and then RNNs, and then he
Unless
just
it's
goes into the
squeezed into one
CNN.
of these, I don't know where it is. We should find it in the 2017 version because the videos are still there.
Yeah,
And make that like homework for.
homework for,
next week or something.
yeah, something it's very good to see that because ultimately all these things are kind of trying to use some previous gradients to improve because the normal stochastic gradient just uses the current gradient and keeps calculating, okay, I'm going to change it based on the current gradient. These other methods, which only, probably 4 or 5 years back, they came up with all this Atom and all that stuff, which just says, okay, can I take some history of some gradients and do either average or decaying average or running, something like that,
Yeah.
and saying, can it be better at updating the weights than just taking the current gradient? So that's all these things are. I mean, they have the Adam, the Eve, and
I've never heard of anybody using Eve. But
yeah, I don't. Yeah, and it's not even, it modifies learning rate based on the recent volatility of loss. So it even changes the learning rate, I suppose. Adapts the learning. Yeah, it's adapts the learning
they're
rate.
all adapting.
Oh, they are all adapting the learning rate.
But they're not
Okay.
adapting the global learning rate. They're adapting the learning rate per parameter. So each
Okay.
parameter is getting a different scaling factor.
Factor. Okay. Okay.
Yeah, lesson 7, he comes back to the CNN. But this is part 1. So I don't know if it might be that one. He talks about Adam there.
Yeah, he talks about Adam, but I don't know if he talks in the
Lesson 7 of 2018.
2018.
This is 20. This is 20. No, this is 2018.
No. If you go here, 2018, I looked at that. I mean, see the lesson wiki. I went through that. I mean, that's where they talk about the timelines and stuff. He goes through. He finishes the RNN stuff, and then he starts pretty much computer vision through this. And I listened to this today, so I know he didn't cover the details of. I mean, he may have said, "Hey, this is more stuff people can." I mean, he has lot more things to cover this time in this. I mean, the RNN is pretty. I mean, we'll come to that. I mean, that he takes almost 1.5 classes to cover the RNNs, and I didn't understand RNN that well. I mean, I knew in principle what an RNN was, but going through his thing, I got to know, okay, how is the weights? I mean, it's kind of, if you think about it, ultimately, it's kind of similar to CNN, but it's different. But you don't keep, because in the RNN, it goes through loop, but it's the same weights again and again. Like that, like the ConNets, you use the same weights again and again as you go through one loop of the RNN to the next loop and the next loop and stuff.
Yeah.
That I didn't understand before. I didn't know that it was the same weights that keeps applying to a layer as a character. Say a 4 characters goes through an RNN. Each character goes through one, either a GRU or an LSTM or one of those linear layers and stuff. Then the next character, it combines with the output of the first one, and then it goes through again. I mean, it's just a loop it goes through, but it's the same weights are applied under each loop. That's something I only understood when I went through this, and he shows how to develop an RNN from scratch and stuff. So that's pretty useful to actually go through this thing on that. But this one, again, yeah, adapts the learning rate per parameter. That's the key. Then you're talking about per weight, it's changing the learning rate based on what happened in the previous gradient versus the current gradient.
Yeah.
Okay. Yeah, I remember going through that in a earlier class. He goes through that in quite a bit of depth at that time. Because at that time, well, that was probably a big thing. And he was going through, because he hadn't covered RNN and stuff in the deep learning first course. I don't think so. Or maybe he covered it, or he didn't cover it in depth.
Yeah, maybe he spent his own time on it.
Yeah, because I remember going through this DE by DB and all that for each of the things. And then he's going and saying, what is my new A? He simulates, yeah, the weights and how do I change the weights and stuff for.
What is E and B?
Well, before we go to the momentum, we got to do basic things here. I mean, the XY is your X and Y.
Just, y equals mx plus b.
V.
Equation.
Yeah.
So here's his equation on H2. Ax plus b minus y
Yeah.
squared. No, I don't know what that is.
No.
Anyway,
That's-
it's just a line.
Yeah.
Slope and intercept.
Because this is the error. He says, okay, this is my X and Y, the real X and Y. And this is I think this is his guess of the intercept and the slope
Yeah, that's
initially.
Yes,
That's what his guess is.
It's way off.
It's way off because if he uses those intercept and slope, he would predict 15 instead of 58. So he's saying that's my error squared here. And then Oh,
found it. It's in lesson 5 NLP. This is the same spreadsheet. I took the note.
oh,
So
okay.
it's in lesson 5 NLP. It talks about.
Lesson 5 could be then lesson 5. If I go there, I can go to the wiki and see where he talks about it. Maybe he talks about it there. Yep. Why a matrix action, not a neural net. Starting the second. What's next? Excel solver. Yep. Well, using Excel gradient descent. That's what I don't think he goes into, because this is the movie lens.
Somewhere.
Yeah, you saw that, but he's just talking for, okay, 10 minutes or something. He's going to be talking about that, I suppose, because
No,
this
that's
goes.
matrix factorization. That's a different thing.
Yeah, that's a different thing. No,
Yeah.
but using Excel solver, no. He just talks about the matrix factorization, how he puts it in the Excel sheet and how he's doing that.
If you scroll up, I think the word SGD is in there. Scroll up a little bit more.
Yeah.
He even mentions this issue. Add SGD.
Ah.
Yeah, that's the issue in PyTorch that's still open. where he fixed it.
Okay.
So if he put that in the notes of the video, then he must be talking
He-
about it in this
In this thing then.
somewhere. So maybe it's further closer to the end or something. Yeah, spreadsheet add.
Yeah, Adam tab, output, okay. Yeah, so,
I want to understand this too a little more, because this part I was a little bit confused.
yeah,
So maybe we can
yeah.
look into this too.
Little bit. I mean, this is the Excel sheet. I mean, this is the simple gradient descent. And so the error squared is 1.8, 1,849. And this one is, what is this? Why is this different? This is C4. C4 is the intercept plus 0.01. I don't know what 0.01 is. Plus A4, D4, okay. A4 into D4, that's a slope, yeah. Minus the B4. Oh, it's just he puts a, okay. He probably wants to do
I
some.
think he needs to remember it, so he has a second cell.
Seconds, no, he just puts in like an epsilon item, like a 0.01 here.
So he increases this a bit.
Oh, he's just doing the D differential.
Oh, yeah.
Yeah.
He's doing the numerical.
Numerical D by dB. Okay.
Okay.
That's what he's doing. Then he's doing it, then he's dividing by 0.01. Okay. He's looking at the intercept. He's just looking at the differential for the intercept. So he's got the intercept, the differential of the intercept here is a dE by dB. And then the error, then he's doing the D4, which is the slope error. Then he's finding the dE by dA. So he's found the differential for the intercept and the differential for the slope. And then he uses, what is the dE by E minus D4? E, Y prediction, minus.
Changing the error over the change of the B term, whatever B is.
Okay.
What's A and B? A and B are
B is
slope and
intercept.
intercepts?
Yeah. D is the intercept, A is the slope. A is the slope.
But then you use M.
Yeah, you know.
I equals M plus B, everybody knows that.
No, he's estimating that. All he's saying is, I don't need to estimate. Okay, I know what the function I'm doing it. He's saying this is what it should be.
Yeah.
He's
Yeah,
just
I don't know why
doing
he
it.
estimates it. I think it just makes it.
Yeah.
Because stats is alpha beta.
Yeah. And then the new A, so he says, okay, I'm gonna now, I know all SGD does this is, hey, I'm taking the old value minus the, the learning rate, the L4, F1 is the learning rate times the L4, the DE minus DA. So that's all it's doing. And the new B is that's all it's doing. It's just that changing it by the learning rate times the differential. And so he changes, when he changes that, then he goes on to the next one. And then he's estimating what this one, he's just taking it from this value, the previous value here. And he's saying, that's my new new estimate of the intercept and the slope, and he's calculating the new intercepts and stuff, and he's just iteratively he's not doing a mini batch as we would do, he's just doing this. So,
Okay, thank you.
and finally he reaches the right solution. He says, this is my solution for the A and the B is, hey, I don't have my error is 592 now compared to what I started off with 1849. I mean, he stops at some point because SGD is not going to give you the exact solution. I mean, it's just each one you're using it to find it closer and closer. And then the momentum is, he's just having the same principle, the D and the DB, and then the new B is this, new A is this, and then he calculates something different here, the J3, J1, what is it? Yeah, he puts a beta factor for both these things.
So I think this is an exponential running average of the gradients
Okay.
with the weight factor being 90% or 10%. I don't know. Depends on how you set up his equation.
Yeah, he says J3 into J3 would be this, is J33. Wow, okay.
It might be worthwhile to show
Yeah.
sort of like what an exponential running average is.
Right, can you write the equation?
Yeah,
Eraser.
That is.
Ah,
I don't know.
which is the veggie? Hey,
This is veggie, I know.
Okay,
Did you only order half? Or did you order?
So let's say
I don't know.
What did you order?
I just
you want a running
push
average.
the button there and it's Mediterranean veggie. I don't know if I ordered a half or I ordered a full.
Oh, that's other half. That's veggie. This is veggie. Yeah. So this is other half of the veggie.
Is this veggie?
Yeah.
No, this is not veggie.
Which one?
This is meat.
Oh, so that's mine.
These are like the time point. So over time,
So
you're
this
getting
is
two
it.
points.
Wow.
And you want to calculate the exponential.
Oh, I don't make the
average.
full half. I think.
So,
There it should be extra, so. This two.
so those are y values, 1496.
Oh, yeah, he got something. I think.
This y
He got
values,
something.
what's that?
this y values.
Yeah.
So just the value
Yeah.
like x by x2, x3.
Ah,
So it's like a time series, a one and a series.
What did you order?
I think this one.
Oh, and your soda?
And also, yeah,
Did you order piecemeal or something?
no, I don't know.
Okay.
It would be bigger, but.
I think you got a half. This is
Oh,
a,
really?
you
Okay.
can order full or half.
Okay, I just clicked.
I have an extra one, because I thought if somebody comes later, so. You know, if you don't need, I will take it home, but if you need, you know, you should be able to. There's bread and.
Yeah.
Yeah, you guys should.
What are you doing?
Oh, no.
So,
Cut the bread for.
We have to have like the first one, the first time.
You want half the bread?
so the exponential running average of a time series is if you choose alpha, some number, it's just the time series at that single point, and then 1 minus alpha times the previous value you used that value.
You need to have.
So in this case, he's choose alpha equals 0.9, so then 1 minus alpha is equal to 0.1. And so basically it's saying, you know, keep 10% of all the previous values. Mostly it's 90% of it is the newest value. But keep history of everything you've calculated up till now. And the reason it's called the exponential moving average is if you actually look at the weights for all the time points, it's this exponential decay, where this is time in halves. And this is, and so for this time period one in the past, you drop down and then it keeps dropping faster and
That's
faster.
not have your initial condition, your initial like average, so 0 or 1 or whatever.
Yeah, you have to put in your A, B, 0 equals X. So you start out with it's exactly what it is, but then for every one after that, it's. And that's all he's doing here in this column. I think.
Yeah,
You can confirm.
because he's doing this running. Well, the only thing that is unclear is he's already having this.
I don't want to.
Oh, you didn't order anything? J33, because he's already saying, hey, I'm gonna make it equal to this last value. So I don't know how he gets that. Because he's saying J3 is this times J1 plus K plus
You were
K1
interested in this, so I can go over it again.
F4 K
So if you have a
times
time series,
F4.
these values up here, I didn't actually run through them, but if you have a time series of data points and you want to calculate the exponential running average of point I in time, then it's xi, that's the value right now, times some coefficient, plus 1 minus that coefficient times the previous average. And that ends up being equivalent to like having a running average where the weights look like this. They dip down. So old values get weighted less in the running average. Like a normal running average would look like this. It would just be a box where you would say this would be, or this width here, N is the width of your running average. So if you had a 10-point running average, it would weight all the previous 10 points equally.
Do you think it's worth watching the video where he explains it?
I don't know if he's doing the momentum. Yeah, we can go there and see what he's exactly, because this is the where I'm getting the thing. Hey, he's already saying J33, but I won't know when I start off what I'm doing.
Oh, so those values come because he runs this over and over. He has like a little macro on his computer.
But I said reset and it's not resetting. I mean, should I just,
I think it just takes those values from the bottom, copies them to the top.
okay, runs it. Okay, if I take this out, I think what he does is, yeah, as you say, it starts with 0. Then he says, okay, I've run it once. Then I can copy this, and then it's probably copying it here. Oh,
I don't know
okay.
how he does it.
You have to run it. I suppose you have to run it. I suppose you run it. Yep, that's what it's doing. You can start off, I mean, you can wipe this out. Basically, he's going back and forth. Like if I do this, you start off with 0. So he's taking the full average of the whole cycle as a starting point. And he's actually assigning, if you look at this, J3 is 0.9.
I
And
think is it not equivalent to just like making a really long spreadsheet?
yeah. Oh, yeah.
Like
Yeah.
he could have just made it longer.
Longer.
But instead, he made it so that he could just hit a button. Doesn't have to scroll.
Yeah, but he's using the same X and Y. He's using the same X and Y. It doesn't change. He's just looping through it.
He's optimizing
Yeah,
A and B
for this X and Y that he has data for.
Yeah.
Yeah, so he's, I mean, he could have repeated itself. I mean, a long thing, he could have repeated
You're
again.
saying that this is a batch.
Yeah, this is a batch.
One screen
It's a batch.
and then he's running the
Batch mode over and over again.
So it's not stochastic gradient descent. This is because if it were stochastic gradient descent, he would be taking a separate mini batch out of the full batch and changing it each time.
Yeah.
I think that's the difference between stochastic gradient descent and just gradient.
Yeah, you would have, this is just gradient design. This is just gradient descent. I mean, this is all he's doing is, I don't know what the value is. He's saying what the average is going to be. So he takes this and says, for the whole thing, he's saying J3 times J1, which is the J1 is this, which is the 0.9, and then the J3 is this. So he's giving more weightage to the average of the whole batch.
So he's got it backwards from what I was
Yeah,
up here.
Yeah.
So his alpha is 0.1
yeah.
and his.
And then he's
alpha is
saying
0.9.
K1 is the 0.1 times the F4, which is the D by dB. So all he's doing is that. And then he's saying the same thing, K3. But here he's opposite, okay? For this one, for the DE by dA, he's doing the opposite because he's saying it's K3 times, K3 times, he's doing the same thing, J1, yeah, he's doing the same thing for both. Yeah, he's just assigning a higher weightage to the average than each point. And then he's just going down the list like that. Like what David wrote.
Increase, right?
No, it still decreases. It's just a matter of, I only give myself 10%, but then I say each previous data point gets 90% of the weight.
And then he says is the last, because this has gone through the whole thing.
Not as.
Influenced by by this thing.
It's mostly the previous average, and I can adjust it.
Yeah. So it's just a moving, exponential moving average with the whole thing. And he's not doing the stochastic gradient. It's just a gradient descent. He's just doing that to each point. And then he's taking at the end of that, he's taking what is my average at the end, and then saying, okay, let me use that as my starting point again.
The difference between different alphas is going to be like, sort of like, this is alpha equals 0.9, this will be like 0.5. So changing the alpha just changes the half-life of your exponential decay. So having a really low value like he has 0.1 means mostly pay attention to the previous points whenever you're updating. Maybe I should just redefine alpha to be on the other term.
Yeah. That's the momentum he's using. The Adagrad is the next one, is it, in his list before you get to Adam, I suppose?
Yeah, so what is Adagrad?
So the X and Y, the D by dB is there, the new B. So that's based on C4. Okay. Minus, that's just normal gradient descent. So F4 minus F4 times, F2, that's different. Okay.
What was this?
So the learning rate is changing or something. He's changing.
Based on that, some function of the average of previous
gradients, yeah.
Not just momentum, but some other.
Because this is what he's saying is D.
I don't know, what is that?
No, he's saying D2 divided by F1. This F1, what he does is, this must be here, the DE and the DB. What he does is, he's taking the gradient and saying that my new learning rate for that parameter is going to be the learning rate divided by even this gradient itself divided by this.
Well, what is that?
This is the square root of this. This is
So that's the root mean square.
root mean square of the DE by dB.
How is that the root mean square?
It's the root and then the sum.
Sum squared by divided by the count.
So it's,
See?
I happen to know root mean square was going to be there. I can't read it. But yeah.
Wait, so what was then F1 and F2 and G1 and G2 then?
Yeah, F1 and
Those are
F
the root mean
squared
of the
error.
previous batch.
previous batch, the whole batch. So he
And then this.
does that, and then he changes his learning rate to be these based on that root mean squared. He says, I got to divide it by that divide the learning rate by this root mean squared to get a new learning rate. And then this also new learning rate. And then he calculates the new B and new A based on that learning rate. And then he will run it more over and over again.
What does that mean, to divide by the root mean squared?
Yeah, let's write it out. See, I mean,
So if the gradients are bigger, then he's gonna divide by bigger numbers, which is gonna make his learning rate smaller if the gradients are bigger? Is that what it's doing?
if to,
Right as the formula.
yeah, if you write out the formula, maybe at least a little. So he's getting the DE by DB, so learning, so you're getting the RMSE of D, what does that DE by DB even mean? RMSE of that. So he's dividing the learning rate divided by that. And then when he's applying this, when he is updating any one of those points, A or B, he's going to say, or B equal to B minus times the D by DB. I mean,
Sure.
they're going to change that.
Where is the,
So here's the D bar, but he's now saying that the error, I'm going to change it, not just by the learning rate times the D by DB, but, so if the error is big, then you're going to change
So
the
it's not RMSE, it's just RMS.
Yeah, it's not RMS,
And-
because it's not an
And in
error.
your mind, you can like
Yeah.
swap out RMS with just the average, take off the sign. It's close.
RMS is,
The root mean squared is sort of like an average, but then throw away the sign. It's like the absolute value.
Yeah,
of the
absolute
average.
value of the
It's not
average, yeah.
actually that, it's slightly different.
It's slightly different,
But
yeah.
it has the
It's an
same,
average.
it's just an average, right? So he's just
Average
taking
of
an
the-
average of the gradients
Yeah,
and he's dividing the learning rate by the average of the gradients. So if the gradients are small, use
Yeah.
a big learning rate. And if the gradients are big, lower the learning rate.
yeah. If the gradients are big, lower the learning rate.
oh wait, the root mean square of
But
all. so this is the
it
root
goes
square
counter
of
thing, isn't it? If the gradient is,
I'm trying to feel like,
It's okay.
but is it going counterintuitive when you do this, when we say, hey, the gradient is thin, we can actually use a bigger learning rate. And when the gradient goes low is when you want to be using a smaller learning rate, isn't it? We usually.
So I think it's the other way around, that when your gradient is really big, you're likely to shoot way past the minimum. Because you happen to be over here and the gradient is really big, if you took that whole gradient, that would put you like way over there. Like, and when the gradient is small, you're in a flat region of the, and if you took only little tiny steps, because it's a flat region, it would take you forever to get there.
Okay, that's the principle they're saying is,
I don't see that.
if you took,
You had another
I don't
question,
see
maybe.
that thing.
Yeah, I thought it was
The opposite,
big steps first and then.
small steps later.
Oh, no, no.
Yeah, that's,
Let's see if this is correct.
because, I mean, the whole point of rate descent is when you know your slope is high, you're steep, then you can jump further off, you know, you'll hit something lower afterwards.
So,
Whereas if you're like in a, not in a steep place, your gradient descent is more slower because it's.
so if you have a function that has like sharp edges and then it gets flat, like doing all kinds of things, there's second derivatives in there too. Thirds and fourth derivatives, right? You have to know all the derivatives in order for you to like actually hit the minimum exactly, right?
Right.
If you knew all the derivatives, you could do it.
Right, like, I mean, if.
But if all you know is the first derivative, then it turns out that you are probably gonna overshoot if the derivative's big. And if the derivative is small, it means you're probably down towards the bottom and you're gonna take forever to get close. I think that's.
No. What I'm seeing, because this is the average of the whole data set.
Yeah,
This
or
is
the
just
previous
DE
mini
is the just, no, this DE by DB is just for that data point.
Yeah. But the
So-
other one is for the whole data set.
Yeah, this one is for the whole data set.
Yeah.
So if, I'm saying maybe the relationship is my gradient for that data point higher than my average gradient? If this is higher, then I apply a greater learning rate.
Yeah, because if it's
I don't think it
higher,
makes any
it's
difference.
higher.
This isn't changing per.
No,
This is only
isn't
changing once,
Yeah,
the
once,
whole
yeah,
thing.
I know, but all I'm saying is this is changing for every data point. This
Sure.
DE by DB is changing. So what, the way it is applying is, hey, if this data point has a higher gradient than the average gradient, then I apply a higher learning rate to adjust this. It's kind of like a higher learning rate. I'm saying, hey, because if this was a
another way
normal
of finding
normal
averages.
learning rate, I would have just applied this, LR times DE by DB. Now I'm bringing this other factor here, which is actually going to slow me down. If I'm bringing
Well, I
this
mean,
other factor.
if you rewrite your equation and just swap these two terms out, right?
Yeah.
Then this is the average, like, and then you sum over all of them, then it would be the average, right? Because this is.
If you sum all
this
of
is
them,
a sum.
but this is just for one. Each one is where the difference is making. This is just for this one. Is it greater than the average or not? Is it lower than the average or not? So somehow, instead of the normal gradient, would just apply learning rate minus the DE by DB for each data point. They're just somehow saying, okay, I don't want to change it by that, but I want to change it by only the average of that.
Well,
I mean, it's a way to smoothen the, I don't know.
assuming we have the equation on the board, right?
Yeah.
What I said earlier is still true.
Oh, yeah,
If
what
the
you said is,
previous-
yeah,
Average gradients are high,
yeah.
then lower the effective learning rate. And if the previous gradients are low,
Yeah.
raise the effective learning rate. Because it's in the denominator, so it's the opposite.
If it's low, then it would be
Yeah, we-
smaller than the root square.
He probably would explain this there or something.
In the current
If you go, have
batch,
to,
you don't get to change it, you just multiply by whatever the gradient is right now. But in the previous batch, where your gradient high and low, if they were high, then your factor is 1 divided by something that's high. And if they were low, then it's 1 divided by something that was low.
Low, which makes it, if it was low, then 1 by something that's low is big.
No, I'm for watching his video. Like, he
Yeah.
does a much better job of explaining.
but I don't know if he's going to explain the AdaGrad. He may go through just saying, I mean, the Adam is the thing he goes on to the
I think
momentum.
He says that he multiplied by the RMS of the previous ones, but maybe
It doesn't look like this one says divided by this one, the F1, and this says it's divided by the G1, and then saying F4, which is this times
I watched it
F2.
a long time ago, so maybe I'm wrong that he says multiples. Maybe he does say divided by RMS.
But does he even go there is my question. I mean, we can go there to his, what was the time thing he gets there?
Yeah.
Oh, no, he had the wiki text here, which was 1 minute 53 seconds is where he's gonna.
An hour and 50.
Oh, I could click on that and it'll take me there. So because he's gonna do the momentum, I suppose, and then
It's like it keeps going the same direction. So it's like, come on, take a hint. That's a good direction. So the come on, take a hint, that's a good direction. Please keep doing that, but more. is called momentum. Right? So on our next spreadsheet, we're going to implement momentum.
Can you maximize that?
Oh, yeah.
So what momentum does is the same thing. And to simplify this spreadsheet, I've removed the finite difference columns. Okay. Other than that, it's just the same, right? So we still got our x's, our y's, our a's and b's, our predictions. Our error is now over here. Okay. And here's our derivatives. Okay. Our new calculation for, let's grab a particular row. Our new calculation here for our new A term, just like before, is equal to whatever A was before, minus, okay, now this time I'm not taking the derivative, but I'm minusing some other number times the loan rate. So what's this other number? Okay, so this other number is equal to the derivative times, what's this? K1.02
He's actually using 0.02.
plus 0.98 times the thing just above it. Okay, so this is a linear interpolation between this row's derivative, or this mini batch's derivative, and whatever direction we went last time. Okay? So in other words, keep going the same direction as you were before, right? But update it a little bit, right? And so in our spreadsheet, in our Python just before, we had a momentum of 0.9. Okay, so you can see what tends to happen is that our negative kind of gets more and more negative, right? All the way up to like 2000. Whereas with our standard SGD approach, our derivatives are kind of all over the place, right? Sometimes they're 700, sometimes negative 700, positive 100, you know. So this is basically saying like, yeah, if you've been going down for quite a while, keep doing that until finally here it's like, okay, that seems to be far enough. So that's been less and less and less negative, right? Until we start getting positive. So you can kind of see what's what we mentioned. Like once you start traveling in a particular direction with a particular weight, the wheel starts spinning, and then once the gradient turns around the other way, it's like, oh, slow down, we've got this kind of momentum, and then finally turn back around, right? So when we do it this way, right, we can do exactly the same thing, right? And after 5 iterations, we're at 89, whereas before, after 5 iterations, we're at 104, right? And after a few more, let's do it. Okay, so it's 102. Plus here. This guy, right? So it's a bit better. It's not heaps better. You can still see like these numbers, they're not zipping along, right? But it's definitely an improvement. And it also gives us something else to tune, which is nice. Like, so if this is kind of a well-behaved error surface, right? In other words, like, although it might be bumpy along the way, there's kind of some overall direction. Like imagine you're going down a hill, right? And it's like bumps on, right? So the more momentum you get up, and it's skipping over the tops, right? So we could say like, okay, let's increase our beta up to 0.98, right? And see if that like allows us to train a little faster. And whoa, look at that, something worth checking into, right? So one nice thing about things like momentum is it's like another parameter that you can tune and try and make your model train better. In practice, basically everybody does this. You look at any like ImageNet winner or whatever, they all use momentum. Okay. And so, back over here, when we say use SGD, that basically means use the basic tab of our Excel spreadsheet. But then momentum equals 0.9 means add in, put a 0.9 over here, okay? And so that's kind of your like default starting point. So let's keep going and talk about Atom.
See, he jumps to Adam. He's not going to talk about Adam.
So Atom is something which I actually was not right. Earlier on in this course, I said we've been using Atom by default. We actually haven't. We've actually been, I noticed we've actually been using SGD momentum by default.
Okay.
And the reason
Oh, I was
is
thinking he was
that
gonna say this about Adam.
Atom has had, it's much faster, as you'll see, it's much faster to work with. There's been some problems because people haven't been getting quite as good like final answers with Atom as they have with SGD with momentum. And that's why you'll see like all the, image networking solutions and so forth, all the academic papers always use SGD with momentum and Atom. Seems to be a particular problem in NLP, people really haven't got Atom working at all. The good news is, this was, it looks like this was solved 2 weeks ago. It turned out that the way people were dealing with the combination of weight decay and Atom had a nasty kind of bug in it, basically. And that's kind of carried through to every single library. And one of our students, Anand Sahar, has actually just completed a prototype of adding this new version of Atom called Atom W into FastAI, and he's confirmed that he's getting the much faster, both the faster performance and also the better accuracy. So hopefully we'll have this Atom W in FastAI, ideally before next week. We'll see how we go very, very soon. So it is worth telling you about Atom. So let's talk about it. It's actually incredibly simple. But again, make sure you make it sound really complicated when you tell people so that we can work it out. So here's the same spreadsheet again, right? And here's our randomly selected A and B again. Somehow it's still 1. Here's our prediction. Here's our derivatives. Okay, so now how are we calculating our new A and our new B? You can immediately see it's looking pretty hopeful because even by like row 10, we're seeing the numbers move a lot more. Right? So this is looking pretty encouraging. So how are we calculating this? It's equal to our previous value of B minus J8. Okay, so we're going to have to find out what that is, times our learning rate divided by the square root of L8. Okay, so we're going to have to dig in and see what's going on. One thing to notice here is that my learning rate is way higher than it used to be. But then we're dividing it by this big number. Okay. So let's start out by looking and seeing what this J8 thing is. Okay, J8 is identical to what we had before. J8 is equal to the linear interpolation of the derivative and the previous direction. Okay, so that was easy. So one part of Atom is to use momentum in the way we just defined. Okay, the second piece was to divide by square root L8. What is that? Square root L8, okay, is another linear interpolation of something and something else. And specifically, it's a linear interpolation of F8 squared. Okay, it's a linear interpolation of the derivative squared, along with the derivative squared last time. Okay, so in other words, we've got 2 pieces of momentum going on here. One is calculating the momentum version of the gradient. The other is calculating the momentum version of the gradient squared. And we often refer to this idea as a exponentially weighted moving average. In other words, it's basically equal to the average of this one and the last one and the last one and the last one, but we're like multiplicatively decreasing the previous ones, right? Because we're multiplying it by 0.9 times 0.9 times 0.9 times 0.9. And so you actually see that, for instance, in the FastAI code. if you look at fit, we don't just calculate the average loss, right?
Okay, this I had a
because
question about this.
What I actually want, we certainly don't
I think
just
this is
report
just for
the loss
display.
to every day match, because that just bounces around so much.
Yeah.
So instead, I
Yeah,
say
display, yeah.
average loss is equal to whatever the average loss was last time times 0.98 plus the loss this time times 0.02. Right? So in other words, the FastAI library, the thing that it's actually, when you do like the learning rate finder or plot loss, it's actually showing you the exponentially weighted moving average of the loss. Okay? So it's like a really handy concept. It appears quite a lot, right? The other handy concept to know about is this idea of like, you've got two numbers, one of them is multiplied by some value, the other is multiplied by 1 minus that value. This is a linear interpolation of two values. You'll see it all the time. And for some reason, deep learning people nearly always use the value alpha when they do this. So like keep an eye out if you're reading a paper or something, you see like alpha times blah, 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 plus 1 minus alpha times
That's
blah,
what
blah,
it
blah,
is.
blah, blah.
It's almost like a watch
It's
these
really,
videos.
it's like, when people read papers, none of us like read every thing in the equation. We look at it and we go, oh, linear interpolation, right? And like, so something I was just talking to Rachel about yesterday is like whether we could start trying to find like a new way of writing papers where we literally read back to them, right? Like it'd be so much better to have written like linear interpolate, blah, 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 right? Because then you don't have to have that pattern recognition, right? But until we convince the world to change how they write papers, this is what you have to do, is you have to look, know what to look for, right? And once you do, suddenly the huge page width formulas aren't bad at all. Like you've often noticed, like for example, the two things in here, like they might be totally identical, but this might be at time t, and this might be at like time t minus 1. Right? Like it's very often these big ugly formulas turn out to be really, really simple when they repackage them. Okay, so what are we doing with this gradient squared? So what we were doing with the gradient squared is we were taking the square root and then we were adjusting the learning rate by dividing the learning rate by that.
Oh, this is different.
Okay, so
It's the same
gradient squared
Same idea though.
is always positive, right? And we're taking the exponentially weighted moving average of a bunch of things that are always positive, and then we're taking the square root of that, right? So when is this number going to be high? It's going to be particularly high if there's like one big, if the gradient's got a lot of variation, right? So there's a high variance of gradient, then this g squared thing is going to be a really high number. Whereas if it's like a constant amount, right, it's going to be smaller. Right? Because when you add things that are squared, the squareds like jump out much bigger. Whereas if there wasn't much change, right, then it's not going to be as big. So basically, this number at the bottom here is going to be high if our gradient is changing a lot. Now, what do you want to do if you've got something which is like first negative and then positive and then small and then high, right? Well, you probably want to be more careful, right? You probably don't want to take a big step because you can't really trust it, right? So when the variance of the gradient is high, we're going to divide our learning rate by a big number, right? Whereas if our learning rate is very similar kind of size all the time, then we probably feel pretty good about the step. So we're dividing it by a smaller number. Right? And so this is called an adaptive learning. Right? And like a lot of people have this confusion about Adam. I've seen it on the forum actually. People are
Yeah.
saying, "Isn't
It's called an adaptive. You want to go back?
Yeah, go back like maybe
20 seconds.
Learning rates for different, it's not going to be big. So basically, this number at the bottom here is going to be high if our gradient is changing a lot. Now, what do you want to do if you've got something which is like first negative and then positive and then small and then high?
Kind of what David
Right?
is saying.
Well, you probably want to be more careful, right? You probably don't want to take a big step because you can't really trust it, right? So when the variance of the gradient is high, we're going to divide our learning rate by a big number. Right? Whereas if our learning rate is very similar kind of size all the time,
Not
then
learning
we
rate,
probably
grading.
feel pretty good about the step. So we're dividing it by a small amount. Right? And so this is called an adaptive learning rate. Right? And like a lot of people have this confusion about ADAM. I've seen it on the forum actually, where people are like, isn't there some kind of adaptive learning rate where somehow you're like setting different learning rates for different layers or something? It's like, no, not really. Right? All we're doing is we're just saying like, just keep track of the average of the squares of the gradients and use that to adjust the learning rate. So there's still one learning rate.
There's a lot of variation.
Okay, in this case it's one. Right?
Surface.
But effectively, every parameter at every epoch is being kind of like getting a bigger jump if the learning rate, if the gradient's been pretty constant for that weight, and a smaller jump otherwise. Okay? And that's
So he's coming from a different angle, saying, I don't trust these
gradients
gradients
Right,
anymore.
so there's now no reason at all why you can't train the internet in Excel, because you've got access to all the pieces you need. And so let's try this out. Right.
So,
Okay, that's not bad, right? 5 and it's like 29.
Right, right. It's not
So the difference between like,
they may be close.
Yeah.
something like the.
welcome back.
Oh,
lesson
I didn't
six.
do that.
It's like high variance on the derivative. I'm trying to understand.
It's like it keeps going in the same direction.
Like,
Whatever the upright.
high variance, that means like. You
mentioned
run
this
this
is the
thing a lot of
process of
times.
creating.
You know, the key difference was that it figured out that we need,
Square
right?
root.
And
I see.
So if you,
Isn't the variance the square root?
even this AdaGrad itself is doing a little bit differently, but where is the Adam here?
What's our list? How is that?
Well, the standard deviation is x minus x squared for all.
Well, no, it's, and standard,
over
the
I.
so the variance, yeah, and then,
Right.
but that, no, it's the mean, and then you take the square of all those, right?
The RMSE is your square root of the gradient.
Is. That whole thing squared, you take the sum of all those.
Finish writing it?
No.
Oh,
When
add.
I think of variance, I always
Add.
think of, I guess, here.
Why?
Sorry.
This is like stuff from.
No, take this, this thing. I need to take one of these and.
Oh, yeah.
Yeah.
That's why they're.
Yeah. That's,
And the standard deviation.
But this is sigma squared
Yes.
and sigma equals.
M5. M5. Okay, the previous value
RMSE is the square root of the
M6 is L1.
In Adam, it's using the gradient.
It's M1
We'll
into-
just call X here. So it's taking the gradient
1 to G7
squared.
1 into
Okay.
G7 squared.
Keeping track of. Square plus alpha times. And then it's the square root of that.
So he's got two parameters now. He's doing an exponential moving of the things. Okay. So the way this is working is, yeah, he's actually got, I mean, he's calculating, here is a normal momentum thing, basically for the A and the B. So all he's doing is I'm doing 0.7 of the previous value, the previous grade, what is it, the J5. J5 is the well, yeah, J phi, that's a previous value times 0.7 plus 0.3 times F6. Okay, so he's calculating the normal, the momentum-based gradients here in these two columns, the momentum-based gradients.
So it's the
Gradients.
gradient of so it's
It's
the
just-
momentum of the gradient.
Gradients of A.
Momentum of the gradient of B.
B, because all he's doing is, hey, what is my previous value times that, and the plus the new the current gradient times the 0.3. So it's just a moment. It's just the exponentially carrying momentum value there. It's just alpha minus alpha times the d plus alpha times the previous value plus the 1 minus alpha into the current gradient, basically. So he's doing that. So that's what he's got these two values for. Then the next one is he's doing the squares of the gradients, basically. A momentum-based square of the gradients. And then he's saying, okay, what's my new B is C6 minus the J6.
If you double click, it doesn't show you the cells or whatever.
It'll show me the cell, but it's very difficult to figure out. Yeah, I can. So C6, I mean, this is going to be your, what is this? This
That's
is,
your global learning rate.
yeah, global learning rate. That's your D2, then the J6, C6, then minus the J6. J6 is your momentum-based gradient. That divided by the square root of the squared momentum gradient. I mean, that's what Adam is supposed, yeah, it's doing.
So it's momentum
Based d by dB
divided
by,
by the RMS.
well, it's not the RMS here. It's a momentum based d by dB square, d by dB the whole square, and then the square root of it.
Square and square root, though, makes you think.
No, because this is a
It's
momentum
not
based.
mean, it's an exponentially weighted mean.
Exponentially weighted squared stuff. Because he's doing the square root after he's calculating the squared momentum.
Mhm.
So it'll be different from your normal.
So it would be like X R,
Yeah.
then this would be so take the square.
Square,
and take the
exponential average, and then take the square root of that.
Yeah.
Square root of that.
Yep.
So he's dividing that by that. So he's saying if that's very high, the squares are high, then I can't, or if the gradient is changing a lot, because he's doing the momentum, if it's changing, hey, I got a momentum here and the next momentum is very different, then my squared is going to change
By a lot.
by a lot, is what he's saying. Compare to this.
So he's
Compare to
comparing.
this.
So,
Comparing the normal, the exponential average of the
yeah,
of the
let's call
X.
this phi,
yeah,
and we have something called theta.
yeah,
We compare this to just,
exponential average of X.
yeah. And so he's saying that if X is changing a lot,
Yeah,
this term blows up faster than this.
faster than this term. So he's gonna then adjust the learning rate to a lower value, because this is what is actually, I mean.
Because it's in the
ultimately-
denominator.
Denominator, it's in the denominator, so it's gonna give it a lower learning rate.
Because you don't trust it.
Yeah.
Yeah, that's where he's coming. He's saying, I can't trust it.
You can jump more,
Yeah,
because it's the same.
it's the same thing. I can trust more, because he's not looking at the learning rate. He's saying, hey, because he's looking at each data point. Is this data point, next I calculate the gradient, is it changing a lot from the
So-
previous data
and it's-
point? So my curve was here and got here, I got here.
This square is the reason that it blows up faster than this one, because
Yeah.
you're this one is changing signs.
Signs.
This stays close to zero.
Close to zero.
Whereas this one, if it changes sign, it still blows up because the square.
Because that's what he's saying. It could be
concept
here
of
and it could be here, and then I can't trust it. And he's saying that's how he's adjusting the learning rate. I mean, that seems to be what the Adam has done. I mean, they must have arrived at Adam based on slowly. Hey, first we saw that momentum thing, where they were adjusting it. The AdaGrad.
Yeah.
I suppose the AdaGrad. The AdaGrad was just doing it not on the.
It's not doing the exponentially weighted average, it's doing it based on the previous.
The whole batch thing, the RMSC here,
Yeah.
whole thing, it was based on that.
Yeah.
And then he was, then now they're in the Adam, they are adjusting every data point, every learning rate, rather than the whole batch, they're adjusting that. So that's the Adam. But he was mentioning, hey, it's been implemented wrong and Adam W. And so that may be the problem you're also facing with your Planet data set.
Well,
Yes.
I don't know, so he's still saying that he's using standard SGD with momentum. Instead of Adam.
And getting the.
So I think that that's what he's doing, but maybe
Okay.
I'm wrong and I've read the code wrong and it's actually using Adam W. and that's why it's
Okay.
better than mine.
And then when I mentioned when we were looking at the momentum, this is actually doing the exponential, what you were talking about. It's like taking the previous value times 0.9 plus 0.1 of the current value is what it is doing. Because I was looking at the first one, that was from the last value. That's just so that it keeps looping around. But this value it's only 0.1 of the current value times the 0.9 of whatever you've accumulated as you've gone through on the DEs.
Well, I hope we have on board everybody else, but this is super exciting.
No, well, I want to understand.
I finally understand all of these spreadsheets now. Like, I was like 85% there.
Yeah.
But now, now I feel like I really.
Yeah.
Well, hopefully,
And match
it just gets fixed in PyTorch.
Yeah.
There's like the PR is there to fix it. It's just like 6 months old.
So I suppose you have to choose two different values in Adam then. How do you choose when he says an Adam, the weight decay, is that just one parameter? Or, I mean, here he's using two parameters.
So yeah.
One
is
for the
of the gradient, and the other is the momentum of the gradient.
the square. So how do you specify that in Adam? When you go to PyTorch, does it have two? Because all I saw was this weight decay, but is that weight decay, what does it represent? I don't even know, what does the weight decay represent?
I have to look through the actual. Now that I understand spreadsheets and what it's supposed to be doing, I can look at the code and find out what it's really doing.
I mean, what is this weight decay in this?
So
I mean, are there
I can
more?
totally mislead everybody, but what I think is happening is L2 normalization is saying for every parameter in your system, divide it by the square of that parameter, like get it closer to 0 all the time.
Here you see, there's
I think
two betas. There's two betas. That's what he's using. So one is for the normal momentum, and then there's 0.999 must be for the squared thing.
Yeah, and so then weight decay is implemented as L2 normalization, which is divide
L2 penalty.
by the mean. Is that what the second?
Yeah, L2 has the alpha. The L2 is where they use an alpha squared or something like that, isn't it? I mean, L1 is where the L2 uses where they are multiplying it by the squared. I thought L1 is where they would do the modulus and then multiply that by the or not alpha. I mean, whatever the L1 parameter is, which they would add as a regularization to this, so that it doesn't. And the L2 I thought was just W of that squared, which is the weight squared, so that it doesn't.
So My
So-
intuition for it is every parameter that you have in your system
Yeah,
that is being updated,
yeah,
the way.
You don't want to
the
go
way weight
too
decay
high.
originally worked
yeah,
was every time you did an update, after you did the update, then like bring it down
Yeah.
closer to zero.
Yeah.
And that if you stop updating something, eventually it goes all the way to zero.
yeah.
Or like really, like, because it's squared, it gets closer and closer to zero, never actually gets to zero. But that's not how it's really implemented. That's what
Okay.
the weight decay,
Because I remember L2 is so that it doesn't blow. I mean, the L2 localization was done so that the parameters didn't blow. I mean,
that's right, yeah.
kept going bigger because this would become big an error term because the W squared. If the parameter went bigger, the error term would
Yeah.
become bigger, and
But
so
I
they
think
try
for-
to bring the.
I think everybody has implemented it wrong though, because instead of changing the weight,
Yeah.
which is what weight decay is supposed to do, they
Okay.
change the gradient every time. And for
Okay.
standard SGD, they're
Yeah.
equivalent because it's linear, like you're doing the same thing
Yeah.
every time. You can
Yeah.
either change the gradients or you can change the weight.
Yeah.
But in this, because it's got all this RMSE and all this other stuff, they're not equivalent anymore.
Yeah.
But they were implemented as though they were equivalent. So
Okay.
here where it says weight decay is L2 penalty or
Penalty?
whatever,
Yeah.
it's
So you just make it
it's actually not.
Nah.
And this is why.
why it is. So
They have this-
probably if you want to use Atom, then you just have to use weight decay 0
Which
without
is
the
the
L2
default.
Yeah, which is
But
the
I think
default.
that everybody gets, like, you don't, you can't use really high learning rates if your weight decay is 0. Because part of your network will blow up and then that will bring the whole network down.
Because the weight decay is 0. Okay, if you can't use a higher learning rate. Okay.
Yeah,
Okay.
and I've seen this too in like these
Okay.
learning rate surveys that I run,
Okay.
like the LR find. Changing the weight decay factor,
Yeah.
it doesn't change it for low learning rates, but for high learning rates, it
Yeah.
stabilizes it so that you can use higher learning rates and still, the network doesn't blow up.
Okay. Okay.
So I think people who want to use Atom want to use really high learning rates,
But they can.
but they can't because
Because of
they
this
try
problem.
to use the weight decay. It's implemented wrong in a
Yeah.
way
Yeah.
that in the end costs you.
Because okay.
Your accuracy.
See, that's what the coefficients used for computing the running averages of gradients and its square. I mean, they're saying running average, but it's, yeah, it is a kind of, I mean,
It's an
it's a running, exponential
average.
running average. Yeah, they don't say it. It's an exponential running average. It's not a normal, it's, yeah. It's a different running average compared to, I mean, a running average would just sum the thing and keep
Yeah.
going without
Yeah,
having
sort
an
of like what I
alpha.
drew. It's just a square
Yeah.
function instead of an exponentially decaying.
Decaying thing, yeah. So, okay. No, this was super useful, at least for me to, like, this spreadsheet and going through this and stuff. There's a weight decay, I mean, I didn't understand. I would just plug it in and see what happens. And stuff. So, but I'm surprised they didn't ever fix it. It's still an open issue.
Still open, yeah.
And we don't know if FastAI has fixed it. You don't know that.
It's really
And
hard to
hopefully-
read through and
Yeah.
figure out what they're doing.
Yeah. Okay.
It's
Cool.
hard to know what optimizer they're actually using. It's not, like in Sconce, it's super clear because you have the optimizer and you attach it to the parameters you want. You do it yourself.
Yeah.
In FastAI, it's buried
Oh, yeah,
underneath
buried
with
under
4
many
layers
books.
of
Yeah.
abstraction. And like,
Yeah.
they're doing it for you, and I don't even know how to dig in to find out what they did.
Yeah.
I mean, I was just
Okay.
running it in the debugger for a while, like just to figure out like what is the value of this parameter now?
No, the one way I was I use the debugger too. And the debugger doesn't work until you put it in a function. You have to define a function and then you have to put one of those debugging, what is it called, the debugger line, which is the,
So in the Jupyter Notebook,
Yeah.
you just say %debug.
oh, okay, I didn't know that. I was using this, which is the debug Python, the PDE.
Yeah.
Yeah.
So I think under the hood, that's what Jupyter Notebook is doing too.
But for that, I thought you had to use something like, what is this? I was thinking, I just want to, maybe there is a much easier way to do that than what I was doing.
Yeah,
Set trace. I was doing the PDB and then PDB set trace, and then I put it in a function, and then when I put set trace, it'll stop, and then I'll say
It's like adding a breakpoint.
yeah, adding a breakpoint and
So
stuff.
I
But
have the fast AI code just sitting there,
yeah,
and then I just go to the part of the code that I want to
Yeah.
put a breakpoint. I just throw an exception, and then
oh,
I
in fact, you went to the
debug.
FastIA code library itself and change it, or
Yeah.
oh,
And
okay,
then
no.
Then I throw that exception, and then when I run with the %debug, it opens up the debugger right where the exception was.
Okay, you're actually going and change the code. All I do was, okay, I go in and say PDB set trace, and I say go through each line of thing, how is it going through, and then eventually I find that, okay, where is it going? So,
Yeah. No, I mean, I knew it was eventually getting to this part of the code where
Okay.
it's doing the gradient updates.
yeah, okay,
And so then I had
Okay.
to open the debugger.
okay, cool. I think this is good. I mean, again, we have to know, I mean, loss functions, optimizer and stuff. I mean, that's ultimately every code we're going to run is based on those 2-3 things. It's the optimizer, and then the learning rate, and then the loss function. I said I didn't know about that binary cross entropy until you told me today, so I'll try and use that.
Yeah.
So
Yeah. It seems
Think
like intuitively that deep learning is really robust against subtle architecture changes, but it is not at all robust against subtle loss function changes. So like changing from one loss function to another,
yeah,
like you get significantly.
oh,
different
significantly
results.
change it, yeah.
But if I changed out,
The optimizer
let's
you
say-
can change, yeah.
let's say
It's
I
not-
added 2 more fully connected layers, I would see virtually no difference in the final outcome. Let's say I added 10 more fully connected layers, it's like, it almost no difference. So like, the architecture of the network, it seems like it makes almost no difference compared to get the loss function right.
Yeah.
For whatever it is that you're.
Get the last one. Yeah. Anyway, we'll come back next week and talk more and stuff. It's just interesting stuff. Like the RNN I've been going through last week. That's super interesting. I never understood, as I said, I never understood the RNN that closely. All I would do is, okay, look at some code and say, okay, throw some code and stuff. But he goes into that, and it's pretty neat to start developing that character by character and stuff. And then he takes you through, okay, there are different techniques you start with. Hey, I want to do 4 characters and I want to do the 5th character, predict the 5th character, basically. But he builds it where you can efficiently do that in a way where you have multi-outputs rather than you don't do it in an inefficient. I mean, you can do this like saying, okay, this is, I'm going home or something. You can say I am, and then you want to predict the next one. And then I can say, okay, the next 3 characters, then I can put it here, A, M, G, and then do the next character and stuff. I mean, you can do that, but that's a very inefficient way of doing this. Is he talks about where I can have multiple outputs coming out with multiple inputs. So what you do is, hey, if you go here, all you do is what's the next, and stuff, and see whether it can predict that whole thing, rather than single output as your prediction. You do a multi-output prediction and still be able to train the model pretty good. If you do a multi-output prediction than a single output, still come up with the same answer as, hey, I want to predict the 4th character, or I want to predict because 4th character means I'm learning what they call the BPTT, is I'm learning from three times recurrent, basically. And,
So we're meeting next week at the
Yeah.
other place, at the CIC.
no, all the time we are meeting here.
We're always meeting.
Yeah. We've got permanent here. Huh?
Or the worldwide.
Yeah.
The Worldwide Tech, I don't even know if I haven't heard from him for some time, so.
Is he on right now?
Usually joins online.
Huh?
Usually joins online.
Yeah.
I don't see him on Slack right now.
I didn't see him on the Slack, so that's what I'm saying is I'm screen sharing. I don't know who else joined. I don't see.
Generic question, like a very naive question too. It's like, I've seen, so we, like, the examples that you show, like, they show neural nets being used, classification patterns, the birds and the dogs and cats, yeah. And then, like, say, like, the example you were showing.
No, he asked me a long time back, but,
Prediction techniques.
oh, Hangout's not working, sorry, he had asked,
Like, neural network, like,
oh, sorry.
value like some like some in a sense.
Well, he should, should give him my number or something, he should have called me, or I didn't even go there, because the thing is, doesn't pop out, I mean, does it pop out for you and tell you there is a new message or something?
You gotta change the settings or something.
Huh?
The settings, so that you get a.
Here, maybe notifications?
Yeah. Well.
No,
Try up there.
notification preference?
Yes.
Is it there?
I was trying to imagine an example that was where that was being used.
Yeah, you should get this.
Enable desktop notifications, allow. Yeah, I need to do that. Sorry, I didn't do this. Direct messages,
Somebody notified you?
yeah. And I didn't look at it.
Oh,
I was gonna choose.
who notified you?
Satya, the guy with the, from WWT.
Oh,
Okay, now
oh
I'm,
yeah, he's on now.
huh?
Catch it now.
No, this is old.
Thanks again for the food.
This.
Yeah, no problem.
Oh, he's still there. Okay, I don't know why the Hangouts didn't work.
Okay, I want an extra.
Okay, someone else will invite us.
That'll be me. That's all. Tomorrow at lunch.
I'm okay with doing it out there every once in a while too.
Yeah, but you guys did. You guys did.
No, it should have worked. I don't know.
Where are you?
I looked at which is close to my house. I live
Oh, okay.
on Stady Road,
Yeah.
Stady and Olive, right next to
I think us three is close by. We live